here, back with some more problems from Miriam and Craig in preparation for exam 3. So we have a seismic instrument shown is attached to a structure which has a horizontal harmonic motion vibration of 3 hertz. So going back and forth, this thing is. The instrument has a mass of 0.5 kilograms and a spring stiffness of 20 newtons per meter. So we already know we can find the natural frequency, and a viscous coefficient, C, of 3 newtons seconds per meter. And the maximum recorded value of X in its steady state motion is this right here, right? So we're recording motion, yeah, but with respect to the housing, right? So that's sort of like a Z thing, actually. We're calling it X here, but I think it's actually a Z. So this is a vibrometer, vibrometer. We're going to determine the amplitude B, right, of the horizontal motion of the support structure right there. So there's your XB. This for us is really going to be Y. So Y is the input. Well, often X is the output, but for us in this case it's going to be Z, because it's going to be relative, right? We're measuring the motion of the thing. We're not measuring the motion of the mass with respect to the outside world. We're measuring it with respect to the housing. That's the big difference. Come back here. All right, so other things they told us was we have 3 hertz, and therefore our omega F is going to be 2 pi times the forcing right there, or 18.85 radians per second. Come back to me. Where'd you go? Boom. Come back to, you did it again. Same mistake. Well, it's because it keeps changing size. It's annoying. Okay, so we have the natural frequency, K over M. Our K is 20 and our mass is 0.5. These are pretty small numbers, so I don't know. We could see in a little bit, we can kind of assess what type of meter this is when we take our R, omega F over omega N, and we see we have 18.85 over 6.325, 2.980. So we're just there, right about of what we say a vibrometer or vibrometer can do for us. Let's take a look at the damping. We have the critical damping of 2 mass times the natural frequency. So 2 times 0.5 times the natural 18.85, and we end up with 6 point, well, this is weird. Somehow we got the same number, but it's just a freaking coincidence, nothing to do with each other. But it's kind of weird to see them right next to each other. So we get a squiggle of a C over CC by taking 3, dividing by 6.325, and we end up getting 0.4743. So we're not using our very favorite damping ratio of 0.7. What haven't I used? I guess I haven't used that blue, so that's fine. So for this vibrometer, which all indications are it's a vibrometer, we can use the R squared over square root of 1 minus R squared plus 2 squiggle R whole thing squared. And so we will plug it in. 2.980 squared over square root of 1 minus 2.980 squared plus 2 times 0.4743 times 2.980, all of that squared. Careful not to make that mistake. And we get 1.061. So it's pretty close. This is really just a 6% error is what we've just observed. But they want to find out if the maximum is determine the amplitude of the horizontal movement, which is going to be our z. So our z is going to be equal to 1.061 times our y, and we were given our y is 2 millimeters. They're calling it x right here. No, excuse me. Whoa, wait. I got that backwards. My bad. We are measuring if the maximum recorded value of x in the steady state motion is this right here. Okay, so this is actually z, and I never wrote that down anywhere here. Z is equal to 2 millimeters. We want to find out what y is according to our way of looking at the thing. So we have y, and we're going to take z, and we're going to divide it by 1.061. Right, so 2 divided by 1.061 is going to equal 1.886 millimeters. And that is what the problem said that it would be. That's a 6.5 minute problem. It's not terribly hard to do. So hope you could do something in that. Do that problem in 6 minutes.